So, well, thank you everybody for sticking around at the end of the day and the extra 10 minutes that I'm late. So what I'm going to talk about today is a current area of research of mine, which I've spent quite the last few years thinking about, that I find very interesting. And it's about propagation of waves through what are called high contrast media. Now, I don't expect anybody here to understand or know what a high contrast media is, and this is precisely why I created this course. So, and it's going to be a very light introduction into what is high contrast media and why we are interested in them from the point of view of applications. Now, for the first few lectures of this course, I will be introducing the subject from a very classical wave theory approach. And the reason I want to do this is because I want to get across the point of the physical interpretation and understanding for why these things are interesting, before getting into the complicated mathematics in which is creating the correct mathematical formulation to systematically study these problems. And the high contrast media is actually a periodic media, first of all. And the reason why we would like to study periodic media is because periodic media, waves propagating in periodic media behave very differently to waves propagating in homogeneous media. And the good thing about discussing waves is we all experience waves in everyday life. It's something quite natural to us, something we've always seen as we were growing up. And you can imagine, a simple example, before I write any formulas or mathematics, let's just think of a little cartoon picture. We have some disturbance, which is some wave propagating through a homogeneous material. And as we know, this will just propagate in a uniform, undisturbed fashion. But then if it comes in contact with an object, so now this is no longer a uniform material, but an inhomogeneous material, then from everyday experience, we know what happens is that the waves will start bouncing off this object and traveling back, maybe going in this direction or in other directions. Literally, it will scatter off the object. And parts of the wave may propagate, but there will be some kind of shadow region here where there will be no disturbance. And actually, there will be some maybe constructive or destructive interference in this direction from the waves. Now, what would happen is a surprising feature that if we had some kind of periodic material now, so we just create some periodic structure, and then the wave starts propagating through this material. Because of these continuous scattering and coherence and destructive interferences, what can happen for waves of certain frequencies is if you're somebody stood here, then this wave will not make it through the material. So the wave cannot propagate through this periodic structure. And this is a surprising feature that we would like to exploit. Particularly, this can happen in the context of electromagnetism, and it gives us an ability to trap light or guide light or localize it within some structure. And of course, we would like to use these in, say, everyday communications like fiber optics, where we want to send some information in our computer down some kind of line. And if we surround our line with some periodic structure, then this information will stay within the line and transmit from one end to the other with minimal energy loss. So why do people study high contrast problems? Well, high contrast problems, for now, and a very formal level, are a type of periodic media. But they are a type of periodic media that have a very strong scattering effect. And you can not only, and so it's quite easy then, in principle, to create an artificial periodic structure that will block waves, not let waves of an arbitrary frequency of our choosing to not propagate or propagate through the material. And the whole, and so the whole purpose of the mathematical study is to answer the interesting question: if I have a wave of a given frequency and I have a periodic structure with given parameters, say the size of the period or the geometry of the structure or the material parameters that make up our composite, can we say when the wave will or will not propagate? And this is a very basic question which motivates some of the mathematics that I will present over the next few lessons. But then there is something even more interesting in the fact that waves do not only propagate or not through periodic media, but there are other interesting effects that can happen. Like maybe some waves can propagate in some directions, but not in other directions. And then can we exploit that in building some kind of artificial structure? So, you know, and then you have this almost science fiction, but something you can understand, this notion of cloaking. So you have a person inside a body, and then you put around it some kind of interesting, say, high contrast periodic composite, whatever this will be for the moment. And then in comes your wave, your electromagnetic wave, but instead of going here, it travels around and then comes out this way. And then if you're a person stood on the other end, then all you see is what was here, and you don't see the object in the middle. And the question is, can we create a composite material that can actually realize this effect? And there are many, and it arguably in experiments in the applied communities, they try to argue these things are possible for certain frequencies, but our goal is to put this under mathematical scrutiny, a rigorous study. But to do this, we need to create a careful, precise mathematical framework to study such a question. So let us begin now with not some pictures, but some formula. And what I first will do is introduce the equations that we will be studying and spend some time describing the behavior of certain types of wave solutions to these equations in homogeneous media before we move on to some periodic media. So maybe I will just write the equations. So first we will have some function, and it will be in the whole space, and it will be a vector valued function into Cn actually, a complex vector valued function. I'll explain why in the moment. And we will look at it solving the following equation: rho ij e squared uj. So the generalized wave equation. So we want to look at solutions to this equation where the coefficients rho are ij, and this is a matrix now, and this is a second order tensor. I won't make any assumptions on these yet because, like I said, for what I'm going to do for the rest of this talk and a little bit onwards is not care about the precise mathematical formula, but just get some kind of intuitive feel across by looking at certain solutions. Now, why am I studying this type of problem? So, well, let's think of some motivations and introduce some particular examples. So the first motivation is acoustics, right? So now we're talking about waves propagating through gas. And actually the propagation through the gas is the particles. And when someone talks, what you hear is a change in pressure. And this change in pressure is what is propagating through the material. Now, do I formulate the equations or do I just write? Okay, let's just, seeing as we lost 10 minutes, maybe you've all seen how to formulate, how to derive the fundamental laws of gas dynamics, but let's just write what these equations are, and if you're interested, you can ask me afterwards how to derive this. So, what do we have? We have V, which is the velocity of the gas particle. So this is the vector. And then we have rho, which is the density of the gas particle. And we have P, which is the pressure. So we're going to study an idealized gas with no viscous terms. And the pressure is only going to be a function of density. So this is an ideal situation, like adiabatic, no work done by friction or heat into or out of the system. And what you realize in the acoustic setting is you have some kind of gas in an ambient state. Say the density is constant, the pressure is constant, and the particles are not moving. And then you have an initial disturbance. And this disturbance creates a small perturbation. In your gas particles, and the acoustic approximation is that V is approximately equal to some. V is approximately a gradient, and what do we have? We have the pressure of x of t is approximately equal to the constant pressure, and then minus the pressure again times by d phi by dt. This density, sorry, and the pressure, same thing for the pressure. And now, okay, I made, because I haven't derived it, I just have to look at the answer. It would have been easier to derive it. So A naught is some value. I can write what A naught is now. And actually A naught squared is nothing more than the derivative of the pressure at rho naught. Okay? And this and this potential phi solves the following equation. Where phi is, I think you've seen it a few times today, but I'll just write it just to make sure everybody's on the same page. Where the delta is the Laplacian. So here we have the motion of the gas particles and the change in density and pressure are all given by this potential phi, which solves the following equation, which is called the wave equation. And this is a version of the wave equation for a special choice of density rho and c. Okay, so the next example. So elasticity, and in fact linear elasticity. Acoustics is like linear gas dynamics, and now we're going to do linear elasticity. So here we have u, which is now the deformation, which is a vector itself. And rho is the density again. And now sigma is the stress, and it follows the generalized Hooke law. Let me write it like this. So this is the stress to strain relation, where the strain is given by this following partial derivative. Xi, right? And the density solves the following equation. I'll write it for each component. Whoops. I could have written it like that, but I'll write it like this. So this is exactly like this equation here. And we'll think one third and final example. So we've done acoustics, we've done elasticity. The last example, let's consider electromagnetism. Could say in these examples, I'm not considering any external force. The evolution is entirely self-propagated. And I will do the same here in electromagnetism. So I will consider a dielectric material where epsilon and mu are the magnetic and dielectric permittivities, and these are 3 by 3 tensors, 3 by 3 symmetric matrices, sorry. And I will let them be invertible, but invertible here. And this is epsilon, right? And E is your electric field. And H is your magnetic field. And now the Maxwell's equations, when we have no free currents and no free charges. We have, and mu and epsilon are going to be functions of x only for for everything I'm going to discuss. So this is the first Maxwell equation. The next one tells us how a magnetic field is generated by an electric field. Then we have no charges, so the electric field is divergent free, and the condition for no monopoles, magnetic monopoles here. So these are the Maxwell's equations. So they don't immediately look like this equation here, right? But let's play with these a little bit. So we'll label some of these equations, label this 1. I'll just label them all. I won't use all the labels. 3 and 4, okay? Now, if we look at 1, the matrices are invertible, so I just do the following trick. Okay? And now I'm going to take the curl of this equation. Okay, I'm running out of, where can I fit it? Oh, sorry, I'll just write it here. No, I'll go on to the next line. And now I'll use which equation? This equation, right? So we have okay, I'll just write it again, all on one line. So we have the following equation. Right? And similarly, you can have the same for the magnetic field, doing the exact same thing. So, but it will be epsilon here, h here, and then minus mu this time. Right? But okay, so you can have the first exact exercise. So these equations, you have to convince yourself did I give it a number? No, right? Important generalized wave equation. So you can convince yourself that the equations 5 look like equation star for just a special choice of the tensor C. Just an algebraic manipulation. But we can say a little bit more. Let's suppose that epsilon and mu are in a special form. They are some scale constant diagonal matrices. And then show that 5, 3 and 4, right? And show that they imply that the Laplacian of E equals epsilon mu. So when we are in an isotropic material, Maxwell's equations reduced to the Laplace equation, and what I mean here is component by component. Each component of the electric field and each component of the magnetic field will solve a Laplace equation for an isotropic dielectric material. So, and this is definitely of this form. Okay, and I forgot to put an exercise in for the elasticity to show that for certain equations it's of this form. No, it's okay. Right, so now we've done some motivations. Let's introduce the type of waves that we are going to study in homogeneous material. So the solutions we are going to study are solutions of the form so they are the solutions of the form here, where K is a vector. What does it need to be? And omega is a number. So let's just get to know this solution structure for the moment. So actually, all of the problems we're interested in, we expect the solution to be real valued. But these problems are linear, and it's mathematically convenient to study complex valued solutions. But actually, the physical solution, so if I just write physical to say the solution, physical solution will be of the following form. It's actually just the real part of this solution. I just write it like this. So the real part of this function is cos omega x, right, minus omega t, plus the argument of AI. But AI is just, I didn't say, right? AI is just some numbers as well. It's a vector A. So what are these physical solutions here? They are plane wave solutions. So they are cosine solutions. And if I draw a picture, we have some kind of cosine profile. Never really good at drawing. Try to convince you here. And what's happening is, ignore the arguments of AI. This is just some phase change that can be ignored. What's happening here is, as x and t change, this quantity is important. And this quantity is called the phase. So if we do some nomenclature in wave theory, in homogeneous material, we have ourselves what is called the phase. And as x and t vary, this value will vary. And what it will do, it will tell you if the solution is either varying from a peak to a trough. So it's describing the oscillations of the wave. And when phi is constant, this will describe regions of constant phase. So for here, this is a constant phase where cosine is, what, 0? And we draw some picture here. And this is a plane. But of course, you can see from here that if phi naught is constant, then this is just a plane, equation for a plane. But what you also will see will happening is, actually, this plane is moving. And this plane is moving in the direction. If I set k to be the absolute value of k hat, where k hat is a unit vector, then these planes of constant phase are moving in the direction k hat. You can see it just from simply playing with this equation and thinking about it for a moment. This phase plane is moving in the direction k hat, and it's moving with the velocity omega over k. And omega over k is the phase speed, and omega over k is the phase velocity. And k is usually, well, some people would call the vector. It depends on the books you read, or whichever way you want to take it. But I'm going to call the absolute value the wave number. But some people would call the vector k the wave number. And this is the wave number. And what does this describe? Well, it tells you in a distance of 2 pi units how many crests, how many peaks of this wave are in a distance of 2 pi. So it's the number of peaks in distance 2 pi, where and omega is the number of peaks in a 2 pi units of time. So lambda, which is the wavelength, is actually 2 pi over k. And t, which is usually the time period, is 2 pi over omega. Okay? And the whole purpose of this study is we want to understand, for a given frequency, omega, are the waves propagating in the direction k hat? And which directions k hat are these waves propagating? These are, in particular, these are the questions that I'm interested in from the context of our talk, if you think back to this little picture I showed in the beginning. But there are other questions of interest that you can ask in waves, and I'll give you some reference to some books in the end if you're interested, about other properties of waves you can derive from these fundamental quantities. And these type of wave solutions are called plane wave solutions. And the reason they're called plane wave solutions is precisely because the disturbances propagate in parallel planes. Because the planes of constant phase are parallel. So now we want to ask ourselves, if we have the wave equation in a homogeneous material, so could there be either acoustics, electromagnetism, or some other realization of the wave equation? For what frequencies omega and for what vectors, directions k, do we have solutions of this form? And all you simply do is you substitute hat Okay, and what do you get? You get the following problem. See, oh. Okay. My subscripts are not good here, right? Because I have too many Ks. Sorry. Let me just think of something else. P, R, R. So you just substitute this in, and all the partial derivatives with respect to x are replaced by k, and partial derivatives in time are replaced by omega. And you end up with a simple algebraic equation, which is an eigenvalue problem. And actually, now I will make some assumptions which hold in all the examples that we studied, and we will assume, say, the following. That this tensor C is symmetric in the following way. And second, thatCijkl x k y l x I y j for now, at this moment, yeah. Oh, what happened to rho? Oh, there was still a rho here somewhere, right? Thank you, actually. Yeah. So I only wrote the density because in the motivating examples there was a density, and of course the density in itself can bring interesting effects into play, but for everything I'm going to say, we're just going to assume that the density is very nicely behaved. Anisotropic maybe, but positive. And in fact, it will disappear very soon. So I would rewrite this because it looks a bit messy. So what do I need here? I need P, right? Okay. And we have these assumptions on our second order tensor. And these assumptions are sufficient for the mathematical framework that we will put it into afterwards. But also in particular, what does it say? So these assumptions, what number shall I have now? So double dagger, right? They imply two things. That Ck is symmetric and positive, invertible. This is a positivity assumption. So what I mean here is Ck for all x. So now the question is, for what's an omega and what k, can I find solutions to this problem? Well, first we will make the following claims. 1, for all omega, there exist solutions of the form in a homogeneous material, right? Second claim, for each and every omega and all directions, and a third important one, which I won't mention so much at the moment here, but maybe we'll get back to later. So before we prove these simple claims, let's think about what they mean. So if I have a frequency omega, then I can always find a propagating wave in our material, which is described by this wave equation. Second, for every frequency omega, you have a wave propagating in all directions. So they just disperse through the material in all possible directions. And third, the wave number is always proportional to omega. This is an important feature that you will see is not true in periodic material and in materials in general that they call dispersive media. And what this, so let's think for a moment. If we had two waves of a frequency omega propagating in a direction k hat with two different values of k. Well, the sum of these two waves is still a solution because our problem is linear. And because this value is proportional, it means that the wave velocity is the same, constant wave velocity. So the two waves will propagate in the same speed throughout the material. But if they were not proportional, so if omega was some strange function of k that isn't linear, then what would happen is as these two waves propagate through the material, one would start traveling faster than the other. And this is the effect of dispersion. But the reason I highlight it here is for another effect that we will see soon in the periodic case. So how do you prove these simple claims, right? Well, first, we remember that k was nothing more than k hat. Okay? And I'll just remind you that k hat is a unit vector. And then we see that ck, well, if you're familiar with the notation, familiar with the terminology, C is a two homogeneous function of k. So if you can see it simply. If I substitute k equals absolute value of k, wave number times k hat, then the wave number squared will just appear outside, and ck is nothing more. I ran out of space. What notation? Oh, C, P, R, K hat is nothing more than C, I, K, P, J, R, L, K hat J, K hat L. Okay? So now this algebraic equation, I can give it a number. I'll try to remember the numbers as I go along, but maybe I'll reproduce some numbers as I go on, which isn't great for your notes, but let's see, this is 6. And 6 now takes the following form. And I'll just write it in vector form. And we want to know when there are solutions to this problem. And I'll just rewrite it now. This is why you can either just set rho to be 1. It doesn't matter for me, and it won't matter for what I say. Or you just, but rho is assumed to be invertible. So rho is a nice matrix. Rho is positive, so that means equivalent to saying determinant is not 0, invertible. So we can just put it on this side. And now what we have is a symmetric positive matrix. And if you remember from your linear algebra theory, this means that this matrix has d eigenvalues. They may not be distinct, but it has d eigenvalues. And so there exists d eigenvalues for each k hat. And d eigenfunctions. What do I want to call these eigenfunctions? What's a good? V. I've been repeating with summation, haven't I? Whoops. So, okay. So this is not repeating here. I'm not repeating with respect to summation. This is just a labeling. Basically, I'm just saying that there are the eigenvalues, maybe not distinct, and the eigenvectors to this for this matrix. So what you can see then is for a fixed omega, So for fixed omega and fixed k hat, you just choose the wave number such that omega over k hat squared equals lambda, right? Lambda I for some I. And then all the three simple clamps will follow. Waves propagate for all frequencies, they propagate in all directions, and the wave number is proportional to their frequency, so that is they propagate with constant phase velocity. So these are the main points for you to remember now when we go on to discussing periodic media. So these are the simple things that happen in homogeneous media. Oh, so I have maybe some more exercises for you to do, right? So you can play with these things. So what's 15 minutes. Sorry? 15 minutes. Okay, well, let's just do some exercises. Introduce periodic problems and maybe carry on next time. So let's think of an example, right? All right, an example. So we go back to the acoustic example. So we have the following problem. D squared phi dt equals a naught squared Laplacian phi. Okay? And we just say phi is some vector. We just take the plane wave ansatz. And what do we get? When the plane wave ansatz, we get omega squared equals precisely k squared a naught squared. So there are two values of omega, and these are given by plus or minus k hat a naught. And you see also, and what you can see here is, make the following statements. Omega over k hat is a naught. So this is indicative, and if you've studied the wave equation before, you will already know this, but for those that you haven't, this is indicative of solutions to the wave equation, and it's precisely why they call this value a naught the wave speed, because the phase velocity is given by a naught. And what you will also notice here is something typical to isotropic materials, which I didn't highlight here because I was discussing anisotropic in general, but something that's particular to isotropic materials, that's when your tensor is diagonal, is that not only is that the phase velocity is independent of the wave direction. So, so these waves propagate with the same speed in all directions, something that isn't true in an anisotropic material. I had an exercise, but I forgot to motivate the example first. So now I'll motivate the example. So we go to elasticity. Actually, isotropic elasticity. I should have written isotropic first. So in isotropic elasticity, it means that your very general Hooke tensor or the stress-strain relation just boils down to a very simple relation. And it boils down to the following relation, which I'll just write for you here. Where lambda and mu are constants, say, for homogeneous material. So this is isotropic elasticity. And so you remember your wave equation, you wrote it down. So show for your deformation that the following quantity solves the following equation. Okay. So the density is now taken to be constant. Just for this exercise, it's not important. I'm sure we have another quantity, call it omega, W, sorry. and this is the curl of the deformation. I'm sure that this solves. What do I want to, where can I write it? Write it here. And I'll write a component. Each component of this vector solves the following wave equation. Right? So this was an exercise that it should have appeared earlier. Now we can think about the plane wave ones. And you can say maybe part 2 of the exercise, show for A parallel to K hat, there exist solutions of the form U I equals A. Oh. Did I do a very bad thing? I did a bad thing here, right? This is quite incorrect. It occurs to me right at the end. I didn't put the variables of the function. Or omega k satisfying what? What do they want to satisfy? So omega squared equals lambda plus 2 mu. Yes, rho naught k. Good. And also go for, so here, what's this exercise telling you? It's telling you for deformations with amplitudes parallel to the direction of propagation, you will have waves propagating with this, this wave speed is given by the square root of this value. So this is the type of wave that you remember all the way back from high school that they call longitudinal waves. So the disturbance is in the direction of propagation. But in isotropic elasticity, you have another type of wave as well. So I don't need to write it all again. I gave it a label, right? So here, now you have, for all omega and k satisfying the following relation, you will have waves whose deformation is perpendicular to the direction of propagation. So these are called transverse waves. So they look like this. If the wave is going in this direction, the displacement is orthogonal to the wave. And another exercise, just to wrap it up, because we had some examples from Maxwell's. So for the case where epsilon is epsilon naught identity, and mu is mu naught identity for constants, so again, no surprise what I'm going to write at the moment. The electric and magnetic field are of the following form, and the velocity this time of these waves is given by the fact, given by the following relationship. So this is 1. And 2, something interesting about electromagnetic waves, what else you can show using the divergence equations. I forgot what labels I gave them, maybe 3 and 4. You can show this, that actually the amplitude of the electric field is orthogonal to the amplitude of the magnetic field. And so they are mutually orthogonal, and they're both orthogonal to the direction of propagation. So you have this picture you may have seen about electromagnetic waves propagating through homogeneous media. They propagate in one direction. The electric field is this way, and the magnetic field is this way. So you can do this. And of course, you will always see that the criteria hold that we just proved. Waves propagate for all frequencies in all directions. And in all three of these examples, we have ourselves isotropic material. So they have this added fact that the wave speed is independent of the direction of propagation. So I think I can finish here for the discussion of homogeneous waves. I don't feel there is any need. I won't be able to go into the next bit. Well, it's a good point to stop, a natural point to stop. And next time what I will do is start introducing the wave equation in periodic material. And then we will start discussing the properties of waves in periodic material. And you will see that all three properties that hold for homogeneous material do not hold in periodic material. Okay, do you have any questions? Yes? Uh-huh. No, this is continuum mechanics. Because I was running a little bit late, I forgot to say, but this is all continuum approximation. And the continuum approximation is no matter how much you zoom in, the material still looks homogeneous. Any other questions? Okay, well then I will see you next morning where we will discuss time harmonic waves propagating in periodic material. Thank you.